Okay, we're going to do the second part of the number theory video now. Mostly this is going to be about the Zn, Un, and the Euler phi function, and then the Chinese remainder theorem. Let's see. I think maybe I did this in a previous video, but I'm going to do it again. If not, we know from before that if n is an element of Z and m is an element of Z plus, maybe m greater than or equal to 2, just to avoid some potential problems. Then we get that there's a unique Q and R such that n equals Q m plus R, and 0 is less than or equal to R less than m. All right, so that was the Euclidean theorem, algorithm, whatever it's called. And this R here, we're calling n mod m, so that's the remainder, right? That's R, right? So this is a function, right? We're inputting in, m is fixed, right? We're inputting in, and we're doing n mod m, and that's the remainder, right? So that's a function. It's literally a function from z, right, to z n, right, which is 0 through n minus 1. We'll actually see another representation for this later, but we may as well just take it to be that. And sometimes we just call this n, right, because we kind of identify a natural number with the set of numbers which are less than the natural number in the natural number, so 0 through that n minus 1. So this is like the, whoops, and I should have said m here, right? M should be m. M is everywhere. M, right? And this would be the the function, which is you input something and then do mod m, right, is a function going from z to zm like that. Good. All right. There's also some relations to define here. So I could have n is equivalent sub m to n prime. So that's one way I'll write this. Another way I'll write this would, okay, so let's just say, what is this? So this is equivalent, this is by definition n mod m equals n prime mod m. Right, and now a little thought shows that that's equivalent to actually saying that m divides n minus n prime. And of course, that's equivalent to saying m divides n prime minus n. The order doesn't matter there. And we also write this thing in other ways, and one of the ways I write it is kind of confusing. So one way that's not confusing to write it would be n is equivalent to n prime mod m, right? So that's kind of another, so this is a little easier to write than that, but these are equivalent. And unfortunately, in my notes, I write this in equals n prime mod m, which is really confusing because now you don't know whether this is, this could be saying n is the remainder, right? But here I'm sort of actually saying I'm looking at this relation, right? So that's, and maybe even you say, well, I take this relation, I apply the mod m to both sides, and so I'm really sort of getting this thing up here. But it's kind of bad. It's bad notation on my part, to be honest. So this would be better. And probably I should just go back and change the notes and solutions, but that's a lot of work. So maybe I'll do it, but it's going to take a while. But anyway, here I'll probably, just to make things easy, I'll probably use this one here in this little talk. But this is a relation, and this is an equivalence relation. Again, sorry for my bad handwriting. So on all of Z. And so, and by the way, what does that mean? It means that it's reflexive, so A is equivalent in A. It's symmetric, so A is equivalent to NB, implies B is equivalent to NA, and it's transitive, so A is equivalent to B, B is equivalent to C, means A is equivalent to C, right? So it's all that. But it also means that we can take Z and break it up into some equivalence classes, right? So one way of writing this might be, I'll tell you what, I mean, so in general, we tend to write for equivalence classes things like this, and how much decoration you put on it here kind of depends on what's what's sort of assumed, right? So I mean, you might just leave out the little decoration there, or I might just put a sub in, and sometimes we also write this like this. And I don't know, or maybe not that. Let's do it like this. Let's say this equivalent sub in. Okay, there's lots of ways of writing this, but basically it's the set of B such that B is equivalent in A, right? So the things that are equivalent to each other. And in general, right, for an arbitrary equivalence relation, right? So, here we have Z, right? And so what we're doing is we're splitting up this Z into some classes, right? And so we're getting these partitions across here, right? And so like, over here, like here may be the class with 0, right? So everything equivalent to 0. And over here might be the class with 1, right? So everything equivalent to 1. And so let's just think about what those are. So like the 0 equivalence class. And in this case, and this is not so normal in general, but for Zn, it's a common thing to do is to put a bar here, right? Just put a bar there. So I could put, what is the class 0 bar? So it's the class containing 0. So it's everything equivalent to 0, right? So that means in or im, here I'm doing sub in. Let's see, yeah, I've gone from sub im to sub in. So this would be all those things so that n divides b minus 0. So in fact, n divides b, right? So this is just the set, 0, n, 2n, etc. And then going the other way, minus n, minus 2n, etc. going that way. And sometimes we might write this as nz, right? Because basically it's all multiples of n, right? That's what it is. So the class of 0 is, in the modulo n relation, the class with the contains 0 is just everything in the form n times z. This is in the mod n, right? N is the thing. So, you could put a little n there, but this is a place where that's implied because n is fixed in this case. What is 1? So 1, the class 1, right, is going to be, the set containing 1. So it's going to be 1, and it's going to be n plus 1, right? 2n plus 1, etc. Okay, and going the other way, it's going to be minus n plus 1, minus 2n plus 1, etc. Going that way, right? And if you look at that for a second, you'll see that that's actually 1 plus nz, right? Or if you like, it's 1 plus 0. So that's convenient, right? That's an easy way of doing that. And then you can just keep going, and you see you keep getting these, and you end up with the class within, you get exactly n classes, because these are the remainders. Those are the only remainders, and then n minus 1 bar. So this would be the class. And that's going to have sort of n minus 1. It's going to be 0 plus n minus 1. It's going to be 2n minus 1. Right, and on the other side, it's going to be minus n plus n minus 1. So it's going to be minus 1, right, and going back that way. All right, and again, this is n minus 1, the number, plus nz, right? Or if you like, it's n minus 1 plus 0. Now, just to be careful, right? What I mean when I do this, and I talked about this in the set theory things, I mean, take the set of everything of the form 1 plus something which is in 0 bar, right? So this is the 0 bar. So if I do 1 plus things in 0 bar, I get exactly the set here, right? And so you get those things there, right? So these are the equivalence classes, right, that you get associated to this equivalence relation. And one thing you should know about equivalence relations is, given a partition, you can define an equivalence relation whose equivalence classes are exactly the elements of the partition, right? So it goes back and forth, partitions and equivalence classes. Now in this case, we get something more. We can actually do algebra on these things, right? So we can define, let's see, m bar plus k bar, right? And so these can be any integers, right? I mean, the way this is defined, these can be anything. And maybe I put an n down here, right? It's kind of implied by the context that we're in right here. But this will just be, the set of all things, so literally using our set theoretic notation, right? This is just the set of A plus B, right? Where A is in M bar and B is in K bar, right? Okay, but that's just the set of all A plus B, where A is in M plus 0 bar and B is in K plus 0 bar, right? And so this is really just the set of all A plus B, where A, is in M plus K plus 0 bar, right? Because if I take something in 0 bar and something else in 0 bar and I add them together, I just get something in 0 bar, right? So we'll see this kind of thing a lot. And so this is in fact just M plus K plus 0 bar, right? So that actually works out kind of nice. This is in fact just M plus K bar, right? So we get this kind of nice fact about the relations. If I take this class and I add it to this class, and sort of in the set of classes, what I get is the class that I would get by just adding M and K and looking at that corresponding class. Okay. Same thing is true for multiplication. So I'm just going to write it here, but M bar times, sub n if you like, whoops, K bar, right? So that's just literally something in M bar times something in K bar. You think about it the same way, and you're going to get that this is M times K product in Z bar, right? So those are actually the same. So we get that kind of relation there. This is equivalent, okay, to the thing that you had to prove in homework. So you had to do this in homework, where you took say M and K element of Zn. Now here, thinking about this as just being 0 through n minus 1, and you showed that M, how was it, M, yeah, what did you actually show? Actually, I think maybe it wasn't quite like that. I think what you did in the homework is more like what I'm doing here. You took M and K and Z, and you showed basically that M plus K mod n is equal to M mod n plus K mod n. You have to be a little bit careful because this might be something, this addition here might still be bigger than n, right? So you actually have to do a final, and I ran out of room. Let me make this a little bit bigger on this side. You might have to do a final mod n out here, right? Because when I add these two things, this may be n minus 1 and that may be n minus 1. So when I add these together, it's bigger than n. So I need to do another mod n right over there. Actually, I guess what you did was slightly different, but kind of the same. But I mean, these two things basically say the same thing here. I guess what you did was a little bit different. It was like if A is equivalent to n A prime and B is equivalent to n B prime, then you got that A plus B n, right, is equivalent to n. In fact, no, so these are just integers, sorry. So this is not a plus in here, just A plus B is equivalent in A prime plus B prime. Right, so that's what you got there. And then same with multiplication. AB is equivalent to n A prime B prime, right? So you got, this was the thing you actually proved, right? Yeah. I guess here, the equivalent statement with the bar things would be this. It'd be A bar equals, now this is a class, so not, this is a relation, or you could say this is a, well, yeah, this is a relation, but between integers, right? But here we have the class. We could replace this with a bar equals a prime bar. Now these are classes. These are each infinite classes of integers, and b bar equals b prime bar, right? And so then we're trying to show that a plus b bar equals a prime plus b prime bar, and a b bar equals a prime b prime bar, right? So that's actually the equivalent. So proving these two things are equivalent to each other. And let's see. So if I had this, let me just think about this for a second. So I would have a plus b bar is equal to a plus b plus 0 bar, right? And a prime plus b prime bar is equal to a prime plus b prime plus 0 bar, right? I want to show that these are the same, right? We're trying to show that a plus b plus 0 bar is equal to a prime plus b prime plus 0 bar, right? So that's what we're trying to show. Let's see if I can do this. So I do have a plus b. I think we can do it this way. Plus 0 bar is equal to a plus, I'm going to do this in a slightly funny way. Okay, I'm just sort of doing this at the spur of the moment. So I can, if I do 0 bar and 0 bar, if I take something in 0 and something in 0 and add them together, and I look at all the ways of doing that, I just get 0 bar back. So as a set, these two things are the same. All right, and so this is a plus 0 bar plus b plus 0 bar. Now here we are using the fact that we have, we're doing, I mean, the actual arithmetic here is addition inside integers, right? So we do have, associativity and commutativity, so I can move things around. Remember, this is describing a whole set of things, this thing plus arbitrary objects in there, right? So, this is this thing plus arbitrary objects in there, this thing plus arbitrary objects in there, and this is an arbitrary one of those plus an arbitrary one of those, etc., right? So these are infinite sets. But now the point is this is a prime plus 0 bar, because those two things are the same. And this is b prime plus 0 bar, because those two things are the same. And so this is now a prime plus b prime. I'm going to just undo what I did up here, 0 bar plus 0 bar. And this is a prime plus b prime plus 0 bar. Okay. So this is, in some sense, a very different looking proof than the one that we kind of went through in class for this one up here, right? So for this one up here, for this one, right? So the way I did this one up here is I said we'll convert this into n divides a minus a prime, n divides b minus b prime, and show that n divides a plus b minus a prime plus b prime. Same thing for the next one, right? So that was using division, right, and using this equivalence relation. Here I'm actually using these objects, which are equivalence classes. So this looks like a very different argument, but essentially somehow the math is the same in there, right? So I'll just sort of leave the nitty-gritty details up to you. Maybe it's worth working through, at least convincing yourself one of these directions. But the point is here is that we've taken this, so let's say we look at Z5, right? So let's just pick an example, Z5, right? So this is 0, 1, 2, 3, 4. Or if you like, we could say it's the classes 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. All right, where here I'm defining the addition like this. Up here we're defining the addition, modulo n, right? So there's kind of two different representations for the same set. They kind of mean the same thing. And you've got to get used to that. We do that a lot in this class. And then we end up with this thing with 5 pieces. 1, 2, 3, 4, 5. Yep, 5 pieces, right? So over here I would have 0 bar. Here I'm going to have 1 plus 0 bar. Here I'm going to have 2 plus 0 bar. 3 plus 0 bar, and 4 plus 0 bar, right? So I get these classes of things, right? So these are again, these are all the elements of z with remainder 0, all the elements with remainder 1, all the elements with remainder 2, right? That's another way of doing this. This is all of z, right? And now we've actually defined an algebra on these, right? We've defined a way of adding these and multiplying these, and so we get a addition and multiplication table. And z5 is kind of interesting because, so let's have plus, let's see, how do I write this? So I have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay, the 0, I'm adding 0, so nothing interesting happens there. I'm adding 1, so nothing interesting happens here, right? So you could almost ignore that part of the table, right? So here's our actual table going on in here. Now here I get 2, 3, 4, 0, and actually these just get shifted, right? 3, 4, 0, 1, 4, 0, 1, 2, 0, 1, 2, 3, right? So those get shifted. So this is the addition table. Okay, and the multiplication table is similar. We didn't drop the 0. 0 times anything is just 0, right? So let's just do 1, 2, 3, 4. And in some sense, we could drop the 1 too, but I'll just keep it here. So we get 1, 2, 3, 4, 2, 3, 4, right? So that's the identity, right? So you just copy that line. Same like this was the additive identity. This is the multiplicative identity. All right, and now we got to think. 2 times 2 is 4. Okay, so that's easy. 2 times 3 is 6, which is 2. And 2 times 4 is, oh wait, did I do that wrong? Nope, 2 times 3 is 6, which is 1, right? 1, right? And 2 times 4 is 8, which is 3, right? And then 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4. And 3 times 4 is 12, which is 2, right? And so notice every element shows up in each of these rows here. 4 times 2 is 8. So that was 3. 4 times 3 is 12, which is 2. This is 16, so that's 1, right? And notice here that this is interesting because, first of all, we never get 0, so no two things multiply together to give us 0, so that's going to be an important fact. And everything has an inverse, so 1 is its own inverse. That's not surprising, but 2 and 3 are inverses, right? 2 times 3 is 1. 3 times 2 is 1. Now, this is, of course, symmetric, right? So you can see the symmetry by looking across there. So that's commutativity in this case, right? Because this is multiplication. 4 times 4, right? So we actually have 4 inverse, or you might write it as 1 over 4, but it's probably better to do it like this because the 1 over notation is kind of bad when you have non-commutative things. That's the reason you don't write, like for matrices, you don't write 1 over A, right? A inverse, right? So think about why we do that. That's sort of why we do this here. So 4 inverse versus itself, right? 2 inverse is 3. 3 inverse is 2. It's got to be like that. 1 inverse is itself, right? It's like that. So everything has an inverse. So in fact, with Z5, everything has an inverse. So this is actually something we'll call a field later on. It actually behaves like the reals or like the complex numbers or like the rationals, right? You can divide, multiply, add, you can do all that stuff. Good, okay, so anyway, that's Zn. What is Un? I see, these videos take longer than I expect them to. Un is the set of all M and Zn such that M inverse exists. So for example, we just saw with we just looked at U5. So U5 is literally 1, 2, 3, 4. So everything except 0. So that would be Z5 star, which is where you just take away the 0, right? But in general, right, when do we have an inverse? So again, this was a homework exercise. What does it mean to be an inverse in here? It means that you have some, or to have an inverse, it means you have some x such that xm is equivalent sub n to 1, right? And so writing this out, what this means is that xm mod n is equal to 1, right? And so that means that xm equals yn plus 1, right? So xm minus yn equals 1. Okay, and this implies that the GCD of m and n is 1. you can't have anything that divides both m and n, because if d divided both m and n, then d would have to divide 1, but the only thing that divides 1 is 1, right? I mean, if the GCD was not 1, right? So this has to be 1. On the other hand, if the GCD is 1, so this is saying, what we just proved is if m inverse exists, then GCD of m and n equals 1, right? On the other hand, right, so that's kind of one direction, if GCD of mn equals 1, then we know from Bézout's theorem that xn plus ym equals 1 has a solution. Let me keep this the same. Let me call it xm plus yn equals 1 has a solution. And then we can mod out by n, and we get that xm equals sub n 1, right? Because if I mod out by n, this just becomes 0. And of course, this means that this implies that x equals m inverse, right? So we actually get that something is an inverse if and only if m is relatively prime to n. So this is exactly the same as the set of all m and zn, such that GCD of m and n equals 1. Okay, and actually I'm just about out of time, so I'm going to have to sort of break this at a place where I didn't expect to. So let me just say one more thing. There's a thing called the Euler-Tauschent function, and so phi n is the size of the set of all m less than n, such that GCD of m and n is 1. In other words, they're relatively prime, right? And so we also know that we could say this is the size of un, right? So it's like that. And I'm going to start the next video by studying this Euler-Tauschent function some. So that's where the next video will start.